Welcome to our microlearning channel. This short video explores the tension between NPU hardware and software development, framing the core question shown on the slide. How does silicon constraints and software complexity balance against each other? The visuals contrast physical Mac arrays and on-chip memory with software stacks and toolchains, and set up our discussion about practical hurdles and potential paths forward in NPU design and deployment. An NPU is a specialized processor built for efficient tensor computation. And this diagram breaks it down into core components, like programmable or fixed Mac engines, on-chip SRAM, DMA, and control logic. It also highlights tensor streaming, sparsity exploitation, and the trade between precision and energy efficiency, and explains how NPUs differ from GPUs by omitting graphics-specific caches and scheduling to boost performance per watt. Smartphone SoC design is a balancing act between thermal limits and performance targets, illustrated here by the 42 degrees Celsius skin temperature constraint versus a 1020 TOPS ambition. The slide shows how dense Mac arrays and GERT switching create power spikes, and why solutions like near-memory compute, fine-grained clock gating, adaptive voltage islands, and advanced heat spreaders are required, despite added cost and tight BOM and form factor constraints. This slide calls out the memory wall. Thousands of Mac lanes can be ready to compute, but stall waiting for waits and activations from LPDDR, which flattens byte per Mac efficiency. The visuals suggest solutions such as on-chip SRAM expansion, HBM-like 3D stacks, processing in memory, aggressive compression, and compiler-driven tiling to reclaim bandwidth and approach efficiency targets through architectural and software innovations. NPU hardware faces rising manufacturing and packaging costs, IP and ecosystem barriers, and an architectural trade-off between flexibility and efficiency, as this slide illustrates. Leading-edge mask sets and advanced packaging add dollars per chip, patented IP can trigger royalties, and fab allocation constrains startups, while programmable engines trade area and lower efficiency for adaptability, versus hardwired engines that need high volume to be economical. Software development for NPUs is fragmented, as shown by evolving frameworks feeding into vendor-specific proprietary toolchains that require forced retuning. The diagram emphasizes how weekly framework updates, unique operators per vendor, and bespoke runtimes create developer burden, leading to retuning work, calibration overhead, and business impacts such as delayed launches and inflated QA budgets driven by siloed tooling. The fallback challenge captures how rare layers not supported by an NPU trigger costly fallbacks to CPU or GPU, producing latency spikes and breaking deterministic pipelines. With mainstream convolutions covering 90–95% of workloads, the uncommon operations create engineering overhead, maintain a fallback whitelist, and demand cross-team effort across firmware, drivers, and runtime to prevent real-time constraints from being violated. This slide summarizes software-specific visibility and tooling problems that slow development. Vendor-specific counters and limited SRAM visibility hide runtime behavior, and opaque intermediate tensors obscure data flow. The consequences are heavy reliance on cycle-accurate simulators and invasive firmware hooks, which in turn slow iterative optimization, complicate field diagnostics, and make debugging accuracy drifts in production much harder. Emerging open initiatives aim to decouple high-level graphs from hardware intrinsics, as depicted here with MLIR, RISC-V vector, and sickle feeding a decoupled middle layer. Retargetable middle ends and portable front ends let silicon teams expose custom ops while preserving front-end portability, and the strategic benefits include faster time to market, shorter software cycles, and better resilience against model churn across devices. The GPNPU concept blends flexibility and efficiency by pairing C-programmable SIMD lanes with fixed Mac arrays in a hybrid compute engine, illustrated on this slide. That hybrid approach lets developers inline new layers without fallback, simplifies single-core execution flow and scheduling, and accepts a modest area cost in exchange for unified toolchains and easier maintenance across diverse workloads. Looking ahead, future NPU architectures will be shaped by experimental technologies and ecosystem decisions. The slide highlights quantum coprocessor prototyping for complex optimization, a chiplet strategy mixing advanced and mature nodes for modularity, and the critical role of standards for interconnect, thermal management, and packaging that will determine which platforms lead in the next decade. Successful NPU platforms require a holistic approach combining early hardware-software co-design, investment in portable compilers, and an integrated software stack that preserves programmability as models drift. The final diagram stresses ecosystem partnerships with fabs, IP, and cloud vendors to sustain value, aiming to maximize AI performance per watt and per dollar through coordinated strategy rather than isolated component fixes.